Hi everyone, my name is Zhiru Zhang. I'm a faculty member of ECE at Cornell. I'm excited to share some of our results and thoughts on machine learning for high-load synthesis. I believe research in this area will become increasingly important. It directly addresses some of the long-standing challenges to how we design hardware in a more productive, also agile way. Speaking of hardware design, this is probably the most exciting time to work on building specialized computing systems. First, the demand is very strong. For many emerging applications, we need them to not only run fast, but also achieve high energy efficiency, especially in the embedded settings. For the time being, the most viable solution is to make use of special purpose hardware accelerators for certain applications or domain. Second, the barrier is also lower than before to start a new hardware project. There is a tremendous amount of leverage since the open source hardware, EDA tools, and software program FPGAs are becoming widely available. But the current hardware design process is still far from productive, especially with the mainstream RTL-based design flow. In fact, iterating and optimizing the design at this low level is extremely slow and cumbersome. This is where HLS, or high-load synthesis, is supposed to help, as it usually takes only a few minutes to compile a high-level program in C++ or System-C into RTL. But there is a catch. HLS tools usually produce inaccurate estimation in QOR, which often becomes a showstopper for achieving design closure at this level. So in other words, there is a strong tension between speed and fidelity with the HLS-based design. And this is already a major issue if you consider the complex design space that we are typically dealing with. Actually, if you just look at the pragmas and TUNAs, so these already form a huge search space. So given all of these advances, right, the recent advances in the machine learning field, it's pretty natural to ask, can we leverage some of the machine learning techniques, right, to address these challenges? For example, is it possible to use ML-based function approximation to improve the QOR estimation at a high level? Also, can we leverage ML to further speed up the design space exploration to automatically configure the tool to optimize our design? Actually, my research group was one of the first to investigate these problems. We studied the gap between the HLS QOR estimates and also the actual results after the place and route. So that's where we collected 60 plus individual designs from the popular HLS benchmark suites like CHstone, Mark Suite, S2C Bench, and Rosetta. We then turned these designs into more than 1,000 data samples with varying clock queries and also target FPU devices. And it actually turns out that on average, the estimation error in resource usage, like lock count and flip-flop count, can be as large as 2 to 4x. This is even using a commercial HLS tool, so which is quite worrisome. We then studied how ML-based QOR inference can help bridge the gap. So this is where we parse the HLS reports to extract a set of design features and then feed them to several widely used ML models, such as linear model, GNN, and gradient tree boosting. So this is where we use XGBoost. So this approach turns out to be very effective. We are able to reduce the estimation error significantly. The bar plot here shows that an ensemble method that combines XGBoost and Lasso, which linear model, works the best. These initial results were published a few years ago at FCCN 2018. So that's where we received the best paper award in the short paper category. But still, there are actually some limitations with this work, as we only use the features from the HLS synthesis report, which does not really include any structural information of the original HLS design, at least not explicitly. In fact, this structural information can be very, very useful, especially for delay prediction. For example, if you target FPGAs, it is important to consider how operations are connected and how they are clustered and mapped to hardened blocks like these DSP units. Such operation mapping can play a major role in determining the performance in terms of both frequency and also latency of the HLS design. So this observation has led to another work that's published at ICCAT 2020. This is where we did the first study of applying graph learning to HLS. Specifically, we focus on predicting whether a cluster of operations mapped to a dedicated DSP block will carry circuitry or soft logic using lookup tables. It's actually worth noting that we did not just directly use an off-the-shelf GNN models like GraphStage. So instead, we customize GraphStage for our purpose. So we can better consider the asymmetric property of the DSP block, where we need to distinguish a pre-adder from a post-adder. The results here, this is actually the model that we constructed. And also the results here show that the efficacy of our customization is indeed obvious. So this is where we look at the accuracy when we train our model. Again, some other baselines like GraphStage and MLP. From these trends, also clear that GNN models are indeed more useful for this task. Okay. So additionally, we show that we can train on a set of synthetic graphs, small graphs, and then test our models on larger realistic HRS designs. And our model shows the ability to generalize, also improves the accuracy of the actual operation delay estimation when we compare it against the commercial HRS tool. The improvements actually quite large. Okay, so given all of these promising results that I just presented, right, for both resource and also delay prediction, it is not really surprising to see that there's this growing broad body of research that uses ML to improve various aspects of QR estimation in HRS. In particular, GNNs have become a popular choice because it can more effectively handle the structural information, like I just mentioned, right? So the connections in the control data flow graphs, those basically those are extracted from the input HRS design. In addition to QR inference, we are also seeing the promising applications of ML on HRS design space exploration. So this is where recent work has explored the use and also various combinations of GNN models, right, reinforcement learning, and also language models. But it's useful to note that currently most of this effort focus on automatically setting the parameters of some of these key HRS optimization pragmas, such as the degree or factor of unrolling, array partitioning, and pipelining. So these to some extent limit the search space. This is something that I'm gonna get to later on. All right, so with all of these encouraging progress, I guess it's reasonable to ask, are we getting close to cracking the problem of ML for HRS? My short answer is not quite. To explain, so let me quickly discuss some of the remaining challenges related to QR inference, time enclosure, and also rapid design space exploration. First, if you look at how the current graph learning models are actually employed in the EDA settings, so this is where we usually directly use the mainstream GNN models that are actually tailored for social networks or citation networks. But these kind of models are not necessarily well suited for circuit graphs. To be more concrete, social networks tend to be homophilic, meaning that the nearby nodes in this graph usually have the same or similar labels. So this is where local structures matters more, since 2 to 3 hop neighbors are usually sufficient for a reasonable prediction, at least the node level prediction. On the other hand, circuit graphs tend to be more heterophilic, where nearby operations tend to have very different properties. Also, the global structures matters a lot more here, since we often need the non-local information to make a more accurate graph level inference or graph level prediction, such as if you want to predict the critical capacity like on a circuit graph. So this is where I really think that there is a ripe opportunity, right, to look at the data set and also to rethink the graph learning models for the EDA problems, of course, including the HRS problem. This is also a topic that my research group is actively working on. Another long-standing challenge to HOS is achieving fast timing closure and high frequency, right? It's actually a very difficult task for an ML model to predict the final critical path at high level, without any physical layout information. Especially these days, right? The critical paths are usually dominated by wire delays. So, there is this abstraction gap. The other thing is that target device is also increasingly heterogeneous. One thing is, there are a lot of different IPs, right? Hardened IPs, which can cause, unexpected routing congestion. And also the newer SoCs increasingly use multi-die integration. And that's where, we have to be really careful with these cross-die wires. The moment, a signal cross-die, so that's where we have to pay a large overhead in terms of delay. And it's usually pretty difficult to predict, right, at high level from HOS, which wire may cross the die without knowing much about what kind of algorithms or what kind of optimizations the downstream flows, right, including physical design flow, may actually do. Okay, so to tackle this challenge, we recently proposed AutoBridge. This is a joint work with Professor Jason Kahn's group at UCLA. This is where we tightly couple HOS pipelining and floor planning. This is really coarse-grained floor planning to improve the frequency of HOS design for FPGAs. It turns out that we can actually improve the timing of many realistic designs. We actually look at more than 40 design configurations of many data flow designs. So out of these 40 design configurations, 16 of them, close to 50% of them, are actually failing timing, failing routing, failing the physical design step. With AutoBridge, so we are able to simultaneously do a high-level pipelining with the floor planning. So that's where we can effectively pipeline the cross-die wires. So that's how we can improve the frequency by close to 2x on average. Okay, I actually believe that there's even more room to further improve by leveraging ML in this space. So this is where we can make prediction, right, at a higher level, at the early design stage, at a coarser design granularity. So we can make a much better prediction of what kind of connection can potentially become a bottleneck, right? The cross-die cross-die communication. This is way easier to do compared to directly predicting at high level which one will become the final connection, the final critical path after place and route. Okay, so this is this is one of the the interesting opportunities, right? Also challenges. So the other one is that even for the DSC, or design space exploration for HOS, there's still significant room. One challenge is that it actually often requires non-trivial manual source level changes to the loop structures of the HOS code and also the data layouts. To give you a concrete example, we can just consider matrix-to-matrix replication, or MADMAR. Now, if we simply do you simply use the conventional, right, the vanilla inner product approach. So that's where we end up with a very slow pipeline, because we're going to be bottlenecked by floating point accumulation. So that's going to increase the initiation interval of the pipeline. We can actually this is right. So this is definitely not efficient. But we can actually leverage a different approach called a row-wise approach, row-wise product approach. This is where we have to use the different loop order and also additional on-chip storage to store the intermediate results. Unfortunately, this is not something that existing HOS-based automatic DSC method can achieve, because, like I said, right, all of this method, they focus on just changing the settings, the factors, the degrees of the unrolling pragmas or pipelining pragmas. It's very difficult for these kind of approaches to do these sort of high level source code changes, source level transformations. So that's where I think there are a lot of interesting opportunities in co-designing the HRS programming model, as well as the, this ML-based auto DSA method, so that we can do this sort of graph level, high level graph level, or maybe initially algebraic transformations more effectively. All right, so to conclude, it's obvious that ML has substantial potential to improve the speed and fidelity of the HR space design. So there are still many challenges, right? Also many opportunities, right, in the area of achieving, good post-layout QR inference, and also achieving time enclosure fast enough, and also enabling this high-quality design specification, where we can actually approach the quality of the manual design. I also see that there are many other promising research opportunities in this area. So first, we can really make use of more HRS-oriented data sets that include both small kernels and also large designs. We could also make use of interpretable ML models for debugging the performance of the HR design, as opposed to just making QOR predictions. There's also an exciting area to explore, so where we can potentially apply ML to further improve the core optimizations within HRS. Again, a lot of interesting challenges and also a lot of room to improve. All right, so I'll stop here. Thank you very much for your attention.